Okay, so in section 12.1, you had some homework problems. You didn't have a lot. You didn't have a lot of homework in 12.1, but you had a few homework problems that asked you to approximate the volume underneath a surface. Okay, and what you had to do was you had to create boxes or bricks uh, based on, and the height of the bricks were determined basically whether you're using, the right corners of the, well, I want to say this even more carefully. So you have to, this surface, the volume underneath the surface, we're talking about a rectangular region in the XY plane. So a rectangular region in the XY plane. Above that is the surface. What's the volume below the surface? And above that rectangular region in the XY plane. And of course, to approximate that volume, you take your rectangular region and divide it up into little subrectangles. And that's going to create then, you can see that in figure 4. And that's going to create then, this is now section 12.1, what I'm showing you here. But you did it in the homework. It's going to create then a bunch of boxes or bricks, and you can find the volume of each brick and add up those volumes and approximate the volume underneath the surface over that rectangle. So what you're really doing here is a double Riemann sum. Okay, the volume is base times width times height. The height of each rectangle is the value of the function at the point you've chosen. Okay, whether it's the left corner, midpoint, right corner of that, times then that's the height, and then the length times width is delta A. That's the area of the sub-rectangle that you're dealing with. So this is a very crude way of computing, of approximating we're approximating the volume underneath the surface, right? But of course, in order for this approximation to be accurate, we have to take more and more boxes or bricks. But just like the Riemann sum in calculus 1, as you take more and more subintervals, the Riemann sum becomes an integral in calculus 1, for the area under a curve. In calculus 3, in multivariable calculus, this double Riemann sum then becomes a double integral. It becomes a double integral. Okay, and so right now, the double integral represents the area under a surface, okay? And you can approximate the volume, I should say, under a surface, and you can approximate that volume. But what if we wanted to find the exact volume underneath the surface? How would we do that? Well, that's where we get into sections 12.2 and 12.3. So 12.2 deals with what's called iterated integrals. And what I want to do actually is go right to figures 1 and 2 in section 12.2 to help make this comfortable for you. Okay, so let's see here. I want to go into 12.2. I'm sure you thought it was amazing in calculus 1 when you could find the exact area underneath the curve. Well, I hope you'll find it equally amazing in multivariable calculus when you learn how to find the exact volume underneath the surface. So, how might we do this? How might we do this? Okay, well, what I'm doing, I'm in section 12.2. And I'm looking at and you can double click on the screen if you want to make the picture a little bigger. I'm I'm looking here at figures 1 and figure 1 and figure 2. Okay, so figure 1, you have a surface and you have a volume underneath the surface. And what they've done is they've taken a cross section there, and the cross section is a function. So I'm looking at figure 1 now. The cross section is a function of x. Okay, the cross section there is a function of x, and they have a of x. A of x. Okay, so let me just, I'm writing something down on paper here. I'm writing something down on paper. Okay, but do you agree that in figure 1, if we were to take that, I mean, do you agree that as we move at, like on the x-axis, the limits go from A to B? On the x-axis, the limits go from A to B. Do you agree as we move, if we pick different values of x from A to B, do you agree that that cross-sectional area A of x is going to change? So the cross-sectional area, okay, good, Ryan, good, Robin, thank you. The cross-sectional area is a function of x, because as we change the value of x, the cross-sectional area is going to change. Okay, it's going to change because the surface is changing above. So if we wanted to estimate, if we wanted to estimate the volume in figure 1 underneath that surface, well, how could we do it? How could we do it? Well, what we could do, and I'll go now to the whiteboard. Okay, and maybe, let me see, maybe I'll try to use my stencil here. Let's see how it goes. What you could do is you could take the area, cross-sectional area, and multiply it by delta x. And this is going to give you a volume, right? Area times, I mean, you got an area, and you multiply it by a width, that's going to give you a volume. And what we could do is we could add up okay, you know, let x sub I be the value of x. Hold on here. And you get, here, you get a Riemann sum. Okay, you get this Riemann sum. And if you take the limit as n goes to infinity, that's going to give you an integral from a to b, okay, of, hold on here, an integral from a to b of a of x d of x. Okay, so far this should be, you know, and you can have your ebook open. Figure 1 is there in your ebook from section 12.2. It probably would be good to have your ebook open because I got to go back and forth. But certainly this is true. But remember what you're doing here. You're, you're adding up a bunch of volumes. Okay, you're adding up a bunch of volumes, and as you take the limit, as n goes to infinity, meaning that you take, as n goes to infinity, meaning you take more and more values of x, you're going to get an integral. But here's the thing. Here's the thing. The a of x, okay, is actually itself an area, and an area is an integral too from calculus 1. An area is an integral too from calculus 1. Oh, what is that area equal to? That area equals the integral of f of xy dy. And then the dx is out here. Okay, so let me just, I always, let me see here. Yeah, so let me just get myself a little more space here. I want to just make things a little bit neater here. Sorry, I'm trying to make it look good. For some reason, I can't get more space on the right. I don't know why, but it's okay. We'll work with the space we got. Okay, so f of xy dy. Okay, so what I'm saying is that this area, which is a function of x, is equal to this integral, the integral of f of xy, that's the surface, integrated with respect to y, where the limits go from c to d. And this is how you get, now you might wonder, well, how can that be, Dr. Duty? Where are you getting that from? Let's go back to the picture. Let's go back to the picture from the book. Okay, so from the book, okay, if you actually look at figure 1, okay, the a of x, I want to say this the right way. I mean, the a of x is an area in figure 1. It's an area. It's an area below the function f of xy, right? F of x, but you're holding in this case, you're holding the x constant, but you're letting y vary from limits c to d. So it's the integral of f of xy with respect to y, where y goes from c to d. And that's how the y, the volume, is then a double integral. That's how the double integral comes about. Okay, that's how the double integral comes about. And the way you evaluate the double integral is the inner integral, you integrate with respect to y, and then you're going to get a function with respect to You're going to then put in the limits c and d, and then the result is you're going to have a function with respect to x, and then you can evaluate that with respect to x. So this is just an example of how this works, and I'm trying to sort of motivate you how this double integral comes about. And incidentally, you can also look at this where your cross-sectional area is a function of y. In figure 2, the cross-sectional area is a function of y. And you let the x vary then. And so you end up with this Fubini's theorem. It's two ways of computing the volume underneath the surface when the bounds are, where your boundaries are like form a rectangle in the xy plane. That's called Fubini's theorem. Okay, that's called Fubini's theorem. Okay, so let's go ahead and look at an example here. Let's go ahead and look at an example. But are there any questions so far? I like this Fubini's theorem because I think it's a nice way to show why a volume is actually computed as a double integral. Okay, if that being said, let's go ahead here and look at example 2. Okay, so here they want you to evaluate the double integral where the region that you're talking about is x is between 0 and 2 and y is between 1 and 2. Okay, so all right, now if we graph the surface, if we graph, and again, double click on the picture if you want it to be on your screen, if you want it to be a little bigger. Even before we look at the solution here, let's look at a picture of this surface. The surface is the function x minus 3y squared. Okay, so if we look at the picture here in figure 3, okay, there is the surface x minus 3y squared over the region where x is between, the rectangular region where x is between 0 and 2 and y is between 1 and 2. Okay, and what do you notice about that surface? What's sort of interesting about the function based on that picture? What's one thing you notice right away? Whoops, let me get that down a little bit. Figure 3. Is the surface above the xy plane or below the xy plane? It's below. Good. Well, if the surface is below the xy plane, what's that going to tell you about the volume? With the volume, so think of the volume between the surface and the xy plane there. The xy plane is on the top where the hold on here, I want to be careful. Yeah, it's on the top there where the origin is. Would the volume between the surface and the xy plane, would it be a positive volume or a negative volume? Let's see. Hold on, Eric has a question. So, well, yeah, well, you see, double integrals can take on negative values just like single integrals can. And when you had a single integral, well, yeah, in this case, all right, yeah. So, but we have to be a little careful. So you can have, remember in calculus when you computed the area underneath the curve, could you have negative area? Could you have negative area? In other words, in calculus, if I go in calculus here, and this is why I'm doing this lecture a little more discussional. So okay, so let's say, calculus 1, here's A, and here's B. Okay, and Jamal, I like what I saw there. So in your comment, one moment here, and there are other comments too. I like seeing the other comments. So this is the integral. I mean, here's your function, f of x, and here's your integral of f of x from a to b. And of course, we know geometrically that's going to be, the value of that integral is going to be the sum of the two areas. And I believe Jamal commented, we have positive area and we have negative area. So is this integral here going to be positive or negative based on this function that I drew? That's right, it's going to be negative, clearly. That's right, Ryan, that's right, Robin, because clearly the positive area is a lot less than the negative area, and you add the positive and negative. So just like in calculus, you can have negative area. I mean, I'm not, you know what I mean. I mean, I'm talking about like in terms of the integral. Okay, I'm not talking like, I'm talking in terms of the integral. You can have an integral with a negative value, and that represents negative area. So okay, all right. So now, okay. Well, we can do the same thing for double integrals. Hold on, let me go back to my thing here. So this problem here, this example 2. Okay, let me double click. Example 2, where we're trying to find this integral here. Hold on, did I lose the book? Yeah, trying to find that integral. Well, geometrically, that integral is represented by this picture here, where our surface is x minus 3y squared, and in this case, it's entirely below the xy plane. So the volume, I ask, is the volume going to be positive or negative in this problem? It's going to be negative. That's right. Now, okay, sure. If you wanted to fill it up with I don't know, liquid or something, then okay, the volume positive. Okay, but we're going to get a negative answer for this double integral. We're going to get a negative answer. And it makes sense. So now when we compute the double integral, okay, here's what you do. Okay, so the inner integral, the inner integral is with respect to y. So just like when you take the partial derivative of a function with respect to y, you hold all the other variables constant. When you do the inner integral, the integral from 1 to 2 of x minus 3y squared dy, you're going to hold the x constant. And so then your antiderivative is going to be xy minus y cubed. And you're going to substitute in, let me go a little bit lower here. Yeah, you're going to substitute in the 1 and the 2. And so then you're going to get x times 1, which is x. And I'm sorry, wait, we have to, now they're leaving out a little bit of a few steps here, aren't they? Hold on, maybe I'll go to the whiteboard here. And let me just, the answer is going to be negative 12, but I think what I'll do is I'll go to the whiteboard and do it out in a little more detail here, since it's your first double integral. So let's confirm this answer. Okay, let's confirm this answer on the whiteboard from example 2. How to, negative 12. So let's go back to the whiteboard. And let me try this. Hold on, class. Okay, so 0 to 2. Hold on, 0 to 2, 1 to 2 of x minus 3y squared dx dy. Now this section, this is example 2, x minus 3y squared. So what I like to do is I like to put x minus 3y squared in parentheses, and then I like to do what's called an iteration. I can only do one integral at a time, so I'm going to do the inner integral first. Okay, and actually, hold on, it was dy dx, right? Dy dx. Oh my gosh, hold on. Oh my goodness, let's try this again. I gotta, hold on, I'm gonna need a firmer surface here. Hold on. Let's try it the old-fashioned way. Okay, so what I do is I iterate the integral. This will be in the recording. In other words, I'm going to compute my inner integral first. Now the inner integral, I'm integrating with respect to y. So I'm going to hold all the other variables constant. Well, the other variable is x. So the antiderivative, x is treated like a constant. So the antiderivative of x is x times y. And the antiderivative of 3y squared is going to be y cubed. And I'm going to evaluate that expression at my limits of 1 and 2. Okay, so far, so good. Are there any questions so far? All right, well then let's continue. So then going up here, have the integral from 0 to 2, and I'm going to put the 2 in for the y. So I'm going to have 2y minus 2 cubed, that quantity, minus, hold on, it should be, sorry, 2x minus 2 cubed, minus 1x minus 1 cubed, okay, that whole thing I'm integrating with respect to x. Okay, so this is going to give me then 2x minus 8 minus x plus 1 dx. And so I get the integral from 0 to 2 of x minus 7 dx. So in example 2 from the textbook, they didn't show all these little steps. Okay, but they're important. And you know your next exam, I'm going to want to see steps because I need to see that you understand the concepts. So I'm going to want to see steps like this. Now it's a calculus 1 problem. And so you're going to get 2 squared over 2 minus 7 times 2. And that's going to be equal, and the 0, you know, comes out, it's 0 there. And so that's going to equal 2 minus 14, which is negative 12. Okay, that's what that's going to equal. All right, are there any questions on that? Okay, if there are no questions, let's go back to the book, back to that example 2. Okay, so all right, so they did it dy dx, but you can also do dx. Hold on, did I lose the book again? Did the book get lost? I don't know what happens with this crazy book. Hold on, class, let me get it back. I mean, it's a good book, it's the best book, but it shouldn't be, you know, conking out on me, you know. Okay, good, good. So double click. So we integrated with respect to y first and then x. But because all of our limits are constants, we can also integrate with respect to x first and then integrate with respect to y second. That's okay to do that by Fubini's theorem. It only works when you have constant limits, okay, for x and y. And sometimes you're going to see you get negative 12 again. Sometimes it's easier to integrate with respect to one variable. It's easier to integrate with respect to one variable first as opposed to another variable. Okay, and that's what example 3 talks about. So may I go ahead to example 3? Are there any questions? Okay, well, then let's go to example 3. Okay, here in this problem, hold on. In this problem, you want to evaluate this double integral, okay, over a rectangular region. So the x limits go from 1 to 2, and the y limits go from 0 to pi. And they say, okay, well, let's first integrate with respect to x. Okay, and if you integrate with respect to x, you're going to get a 0. But again, I think it would be helpful if perhaps I showed it on the whiteboard what they're doing here. Okay, so let me just write down the integral, the double integral, for example 3. Okay, and let me go to the whiteboard. How many find the whiteboard helpful when I show it a little bit on the whiteboard? Show a few more details. Is that helping you? Okay, thank you, Jamal. Thank you, John. Thank you, Robin. Excellent, excellent. All right, well then, here we go. Okay, so example 3. We go from 0 to pi, and from 1 to 2. We have y times the sine of x times y. Now, they are doing it this time dx dy. They're doing it in that order. Okay, so of course, what I'll do, stay away from that eraser, is I'll iterate. Iterate allows us to do it one at a time. Okay, so now, okay, we need the antiderivative of y times the sine of xy with respect to x. Well, all right. The y is held constant. The antiderivative of the sine is the cosine, or I should say minus the cosine. Okay. All right. But we have to divide by y for this antiderivative. I use a lot of grouping symbols to help me. So if you take the partial derivative, of negative cosine of xy over y, you're going to get back the sine of xy, because the derivative of the cosine is minus the sine, and so minus the sine is plus sine. And then by the chain rule, the derivative of x times y with respect to x would be just y, and that y would cancel out with this y in the denominator. So that's the correct antiderivative. Okay, and if we continue here now, well, the y's cancel, and we're left with negative cosine of 2y, because we're substituting 2 in for x. Remember, the first integral is with respect to x. We're holding the y constant. Okay, and then that's minus a negative cosine of 1y. Okay, and all of this here. Okay, and so we're going to get here a negative cosine of 2y plus a cosine of 1y. That's going to be your integrand. Are there any questions so far? All right, well, now it becomes a calculus 1 problem, right? Because we only have one integral. So the antiderivative of cosine is sine. So we have sine of 2y over 2. Don't forget about that minus in front there. Okay, and then we have plus the sine of y. Okay, from 0 to 2 pi. And this is going to equal then negative the sine of 4 pi, because 2 times 2 pi is 4 pi, over 2, plus the sine of 2 pi, minus just pi. Thank you, Robin. That's right. Wait. Hold on. Wait. Oh, my limit was pi. Sorry. Thank you. My limit was pi. So let me fix that. Yeah. See, the mouse is better for the eraser. The limit is pi. So I have negative times the sine of, I don't really need parentheses, you know, but negative sine of 2 pi plus the sine of pi, minus negative sine of 0 over 2 plus the sine of 0. And wow, this is just going to be equal to 0, isn't it? It's going to equal 0. Okay, take a moment to look at it there. One moment, I'm just checking something here. One moment here. Okay, that's fine. That's fine. These are good examples. Are there any questions? Okay. Okay. Well, so that's interesting. What's going on here? We got we have this surface y times the sine of xy, and we're finding the volume underneath the surface, and we end up with a volume of 0. So what happened there? Well, if we go to the book, hold on, I don't think I want to do that. Hold on. I'm going to get the ebook up here where we get it here. Share application. Yeah, if we go to the book here, here's a picture of this surface y times the sine of xy in figure 4. And you can see that the surface is above the xy plane and it's below the xy plane, right? You can see that. And in figure 4. And so there's volume above and volume below, and by symmetry, the volumes, the positive and negative volumes cancel each other, and that gives you 0 volume. That's right, Robin. That's exactly right. Volume above equals volume below. All right. Now, an interesting question too is, what if you were to change your order of integration? What if you were instead, again, the limits here are all constants, so it doesn't matter the order that you do your integration. But if you integrate with respect to y, then this integral, the inner integral from 0 to 2 pi of y sine of xy dy, you're going to have to use integration by parts to do that integral. You're going to have to use integration by parts, and you can do that. You can do that, and if you work it out, you'll end up, if you go through all the steps, you'll end up with 0. It's just a lot harder to get to the 0. So considering the order of integration is always helpful when you do your integration. It's always helpful. Okay. Are there any questions on that? Okay, let's look at one more example here from the book. Okay, let's look at one more example. Example 4, that's the one I want to look at. In this example, okay, they want you to find the volume of a solid that's bounded by the elliptic paraboloid. It looks like a football, right? And the planes x equals 2, y equals 2, and the 3 coordinate planes. Okay, so sometimes you'll have problems where you have to compute the volume and you have to figure out what the limits are. So, in this problem, you're not given the limits. You're not given the limits. And you have to come up with the double integral. Okay, well, so, okay. Are the planes x equals 2 and y equals 2, are those planes vertical planes or horizontal planes? Well, let me ask you, yeah, they're vertical planes. So a plane like z equals 2 would be a horizontal plane, but these are vertical planes. And they cut this paraboloid, and as a result, you're going to get a volume. So this is a picture in Figure 5. This is a picture of our surface. Well, what is the surface? The surface is going to be based, since the paraboloid, the plane's bounded below by the volume's bounded below by the xy plane and above by the paraboloid. So we can write the paraboloid as z equals negative x squared minus 2y squared, right? We can do that. And we could use easy surf to graph that. And this would be what we would get. We would get a surface like this. I mean, you're having some in the MATLAB assignments. You're having practice graphing some surfaces. There's a surface, and it's cut. There are two vertical cuts: the plane x equals 2 and the plane y equals 2. And so that's going to form a rectangular region where x goes from 0 to 2 and y goes from 0 to 2. And that's above the volume above that, and underneath the ellipsoid or elliptical paraboloid, or I'm sorry, elliptic paraboloid. That's going to be, so this isn't a football. I was thinking of ellipsoid. No, this is an elliptical paraboloid. So, right. Okay. So this is going to be then your double integral. This is going to be your double integral. So here the key was you have to find the limits. You have to find the limits. And turns out the volume is 48. Okay, one moment here. Are there any questions on this? Are there any questions regarding this problem? This example? All right, very well. Let me stop the recording.